So we're finally on to our final equilibrium constant for this topic, and that is Kd. And it's called Kd because it refers to the distribution. It's the distribution constant. The equilibrium constant with respect to the distribution. And it's all about a solute dissolved in two solvents that are immiscible. So two solvents that do not mix, and that's explained here. So the easiest way to think about this is if we draw a diagram. And so think about a separating funnel. Imagine you had a separating funnel. Thing you probably think of first is the idea of oil and water. This is more about organic solvents and aqueous solvents. So if we draw our organic solvent on top, generally organic solvents tend to have a lower density than aqueous solvents, so they tend to form the top layer. So we'll shade that in yellow to show that organic solvent. So this is the organic layer. This is the aqueous layer. And this represents a separating funnel. So say I want to now dissolve a solute in these layers. The solute will have a different solubility in the aqueous layer than it does in the organic layer. We know that some things dissolve better in aqueous solvents, like polar salts dissolve better in aqueous salts. Polar, and remember the term like dissolves like, so polar solutes will dissolve better in polar solvents, and organic substances tend to dissolve better in organic solvents, non-polar solvents dissolving non-polar solutes. But it doesn't mean that a solute will be totally insoluble in one layer and fully soluble in another layer. So if I dissolve, say for example, X will distribute itself between the two layers. So yes, it will dissolve better in one layer than another, but we will see that there's a certain concentration of X in each layer. Say for example, we first dissolve it in the aqueous layer. We'll find that we have a certain concentration in the aqueous layer and a certain concentration in the organic layer. So we start with a whole amount of our solute X, but it will distribute itself between the two solvents. What we find is it doesn't just distribute itself and then sit there happily. We find, as with our other equilibrium reactions, that there is an equilibrium going on here. That the solute X will be moving across that border, if you want to see it as this border here between the organic and the aqueous layer. It's dissolved in the aqueous layer, but then maybe some of it will move into the organic layer, and equally some of it will move from the organic layer into the aqueous layer. So we see that while it looks like the concentration is constant, and the concentration is constant in the organic and the aqueous layer, but that's because solute X is continually moving across that border. And as it explains in your notes here, the rate at which it's moving across the layers, or across that border between the layers, is equal. Okay, so we've dissolved solute X and it's moving across these layers, but an equilibrium will be set up to show us the kind of ratio between how much solute is dissolved in the organic layer and how much is dissolved in the aqueous layer. So that is all summarised in what we call the partition law, or the distribution law, where our Kd comes from. And the partition or distribution law states that the concentration of X in both of our layers is constant but it is constantly dissolving and moving between the two layers, just like with our normal equilibrium. The concentration doesn't look like it changes overall, but the reactants are continually reacting to make products, and the products are continually dissociating to give us reactants again. A bit like our busy restaurant. Looks like it's always full, and it is always full. The concentration of people in the restaurant stays the same, but there's constantly people coming in, having their food and then leaving and being replaced by more people. So that's what we're saying with this. And what we can do is KD is simply a ratio between the concentration in the organic layer to the concentration in the aqueous layer. And so what we say is we have a very simple formula for KD, and that is that it's the concentration of the solute in the upper layer over the concentration of the solute at the bottom layer at equilibrium. And it can be simplified by this. And as we said, generally organic solvents have a lower density than aqueous solvents, and so that means they tend to form the upper layer. So we can simplify that to KD is the concentration of X in the organic layer over the concentration of X in the aqueous layer. And that's written down below at the bottom of page 49. So why is this equation the same as this equation? Well, it's because the organic solvent usually has a lower density and so forms the upper layer. So as I've mentioned, KD is simply a ratio of how soluble it is in the organic layer compared to how soluble it is in the aqueous layer. What we find that is that if it's more soluble in the organic layer than the aqueous layer, we'll end up with a KD value of greater than 1. If it's more soluble in the aqueous layer, that means the bottom of our fraction will be larger than the top of our fraction, and so KD will be less than 1. And if our solute has fairly similar solubilities in the organic layer and the aqueous layer, KD will be roughly equal to 1. Now there are a few changes that we need to make on page 50, just because the explanation I've used is using a different representation of KD. So you can see here I've talked about it in terms of A as our solute, but where our equation looks at X as a solute. So if you just take out this whole first part of the sentence and instead write, if X is much more soluble in the organic solvent than the aqueous solvent, then KD will be considerably greater than 1, just as we've discussed. And then there's a sentence at the end here that we know that as temperature changes, so will solubility. So that means that KD is going to change as temperature changes. So the value of KD will change, as we've seen before, as temperature changes, and it's perhaps easier to see with this. And that's because solubility changes with temperature. Generally, if you have a solid, the solubility of that solid will increase with temperature. Think about a cup of tea even. If you have a cold cup of tea, you won't be able to dissolve as much sugar in it, and there'll be lots of sugar sitting at the bottom. Whereas if you've made a cup of tea with boiling hot water, you'll get lots of sugar dissolved in it. And there's a note here on the units of concentration, and the change we need to make here is take out this second word must. So when we're using concentration values for Kc, they have to be in moles per decimeter cubed. But what we find with Kd is that we generally have them either in grams per decimeter cubed or grams per centimeter cubed. We don't have to convert that to moles per decimeter cubed, simply because when we're converting from grams into moles, how do we do that? Well, we use the equation moles, or N equals mass over RFM. When we're converting to that, we'll have a concentration for our organic layer and a concentration for our aqueous layer, but they'll be both in terms of the concentration of our solute X. X is obviously going to have the same RFM, and so when we've got, think of it as KD is mass over RFM divided by mass over RFM. Our RFM is going to be exactly the same, and so they cancel out, and so we can keep our concentration values as grams per centimetre cubed or even grams per decimetre cubed. The only thing that has to be constant is the units of the volume, so whether it's in centimetres cubed or decimetres cubed, that needs to be the same. So how do we find out KD practically? You don't need to worry too much about this. This will actually make more sense when we look at the second practical method in a couple of pages. But what you do is you get your solute X and you dissolve it in either water or your organic solvent. Then you simply add a known volume of your other solvent. So if you started with water, then you'll add a known volume of organic solvent. If you started with your organic solvent, then you add a known volume of your water. You shake the two together in a separating funnel and allow them to settle, so allow the two layers to settle. Remember, they're immiscible, so after a while they will settle and form two layers. Then what you want to do is take a sample from each layer and titrate it. Use titration to get your concentration of X. Once you've got then your concentrations of the solutes in both layers, then you can use your equation of KD equal to the solute of X in the organic layer over the concentration of X in the aqueous layer. You would never have to do that, but you do need to be able to recall that. They might ask you how you determine KD practically. And it's worth mentioning at this stage about the units of KD. What we find with KD is that it never has any units, so it cuts that part out of our calculations. And look at your equation there. You've got the concentration of X in your organic layer over the concentration of X in your aqueous layer. What are the units of concentration in your organic layer? Well, they're more than likely going to be grams per centimetres cubed. The concentration of X in your aqueous layer is again going to be grams per centimetre cubed. And so these just simply cancel out and you end up with no units. You don't need to state it as no units because KD will never have any units. Again, that comes from the idea that KD is simply a ratio of the concentration between the two layers. So because KD is simply a ratio, hopefully you'll find that the calculations involving KD are a little bit more straightforward. And the very simplest case is if you're given the equilibrium concentration in each layer or the equilibrium mass in each layer, in which case you have to first calculate the concentration in each layer. And that's very simply done using this equation. Concentration is mass over volume. So we would normally use the equation as concentration is the number of moles over volume. But as we discussed on the previous page, we can use mass instead of the number of moles. So concentration is mass over volume. So let's look at an example of this. So what we see is that substance X, that's our solute, is shaken with a mixture of ether and water. Ether is an organic solvent. And obviously water is your aqueous solvent. I can just write that. Okay, we can see that the ether and the water layers have different volumes. So the ether layer is 20 centimetres cubed and the water is 10 centimetres cubed, and that's why we need to work out our concentration of that first. So you'll see that our values down the left hand side are a little bit different. We've got the equilibrium mass, the volume of the solvent, and the equilibrium concentration in this case. And this is a very simplest example, and all we have to do first of all is fill in the values that we've been given. So you can see that, let's look at the ether layer first of all, which is the organic layer. So the organic layer contains 6 grams of X. So we simply write 6 grams of X, and its volume is 20 centimeters cubed. 20 centimeters cubed. Okay, then for the aqueous layer, which is water, we can see that it contains 4 grams of X, and its volume is 10 centimeters cubed. Equilibrium concentration is simply mass over volume. So for our aqueous layer, that's the mass of 4 over the volume of 10, which is 0.4. For the organic layer, that's the mass of 6 over the volume of 20, which gives us 0.3. Kd is simply then the concentration of X in the organic layer over the concentration of X in the aqueous layer. Plugging our values in of the concentration, we get that is 0.3 over 0.4, which gives us a Kd ratio of 0.75. We can see that because that is less than 1, our solute is more soluble in the aqueous layer than it is in the organic layer. But that is it. Simply work out your concentrations in each layer and then put them into your expression of Kd. The calculations are slightly more complicated if you're given the initial masses rather than the equilibrium masses. So this would be a case of if all of our solute was initially dissolved in one of the layers and then shaken with the other solvent, and then it would distribute between the 2 layers. But it's still fairly straightforward in comparison to our Kc and Kp calculations. So you can see that we've got a little bit more down the left hand side, and we've just added initial and reacting mass, just as we would have done with Kc and Kp when we were given initial concentrations rather than, or initial moles rather than the equilibrium moles. Okay, so we've got our headings of X in water and X in ethoxyethane. Ethoxyethane is our organic solvent. Just a little side note, ethoxyethane is the same as diethyl ether, which smells lovely. It's simply ethers, or if you have an oxygen in the middle and then an alkyl chain on either side. So diethyl ether means oxygen with an ethyl group this way and an ethyl group connected on the other end. So diethyl ether. So our initial mass of X in water is 1 gram. So we've 1 gram in 100 centimeters cubed of water. So if it's all fully dissolved in water, first of all, our initial mass of X in ethoxyethane is going to be 0. We can see then that at equilibrium, we have 0.8 grams of X in ethoxyethane. And so I'm going to put my equilibrium mass of ethoxyethane as 0.8 grams. Thinking about my reacting mass then, I must have gained 0.8 grams of X in ethoxyethane. Remember, the equilibrium is initial plus reacting. And the ratio of the reacting masses in these calculations is always going to be 1 to 1, which means that I've lost 0.8 grams of X in water. And think about this logically. I had 1 gram of X in water, and then I shook the two layers together, and now 0.8 grams of it is in ethoxyethane. That means I must have lost 0.8 grams from water because it was initially all in water. That gives me an equilibrium mass of water as 0.2 grams. The total of our equilibrium masses should always equal the initial mass of my solute. So I had 1 gram of my solute. I'm not making more or losing any of X, but it's just distributing between the two layers. So you can see that 0.2 grams plus 0.8 grams gives me my initial 1 gram. So I now need to write down the values of my volume of each solvent. You can see from the question that I have 100 centimetres cubed of water and just 25 centimetres cubed of my ethoxyethane. Equilibrium concentration can be calculated by doing mass over volume. So for X in water, 0.2 grams over 100, which gives me 0.002, or 2 times 10 to the minus 3. For the equilibrium concentration of X in ethoxyethane, it's going to be 0.8 divided by 25, which gives me 0.032. Now all that's left to do is put these concentrations into my expression for Kd. So remember that Kd is going to be the concentration of X in your organic solvent. In this case, it's ethoxyethane, over the concentration of X in your aqueous solvent, which in this case is water. Plugging in my values then, concentration of X in ethoxyethane is 0.032, concentration of X in water is 0.002, which gives me a value of Kd as 16. And we can tell from this value that X is far more soluble in ethoxyethane than it is in water. Solvent extractions is something that is used widely in preparation of organic substances. And how it works is, if we have a beaker containing an aqueous solvent, for example water, and we've got substance X dissolved in it. And say substance X is an organic substance, so it's more likely to be more soluble in an organic solvent than in an aqueous solvent. I would want to extract X from that aqueous solvent. But how would I do that? Well, how I would do it is I would add in some organic solvent. So I'm going to draw that again using yellow. So I'd add in some organic solvent. If I was then to put this in a separating funnel, put the stopper on it and shake the separating funnel, then X would distribute itself between the organic and the aqueous layer. So I'd have a certain concentration of X in my aqueous layer and a certain concentration of X in my organic layer. So some of it has moved into the organic layer, just as we saw in the previous calculation. If I then wanted to get X, I could then simply put these in a separating funnel and run off the bottom layer. So the bottom layer is going to be this aqueous layer. So I'll end up with a layer of X in an aqueous solvent. In a separate container, then I would run off the organic layer, which would be X dissolved in my organic solvent. This is the layer that I want to keep. I want to keep my X, which is an organic solute, dissolved in my organic solvent. But what you can see is there's going to be a certain percentage of X still dissolved in my aqueous solvent. So what I can then do is put that back into a separating funnel. My aqueous solvent in a separating funnel, which will still contain a little bit of X, and then add in some more organic solvent. Again, I would shake it, and some of X would move into the organic layer. Again, I would run off the bottom layer, which is the aqueous layer, which is still going to contain a little bit of X and a little bit less now. And then I would run off into a separate container, the organic layer, which contains a little bit more of my X. What I can then do is add the organic layer I extracted here to the organic layer I extracted here. Combine those two, and that gets me the solute X in the solvent that I wanted. If I wanted, I could then take the aqueous layer and add some more organic solvent to it and extract more of X. But the principle I'm doing this by is I'm adding in my organic solvent, which X is more soluble in. When I then shake it with the aqueous layer, more of X will move into the organic layer than it does in the aqueous layer. So it's because based on the principle that X is more soluble in an organic solvent than it is in an aqueous solvent. So it's moving from that aqueous solvent into the organic solvent layer. And you can keep doing this until you extract more and more of X. And down below is a little a summary of that method with just a few more practical details. For example, step 3 is invert and open the tap to release any pressure. That means turn the separating funnel upside down, obviously with your stopper at the top, and then open the tap in it. So think a separating funnel like something like this. Okay, so I'm turning that upside down and then opening the tap. This is the tap here. That's because as we shake these two layers together, there will be a certain amount of pressure building up. And so I want to release that pressure, release the gas by opening the tap. But obviously I need to turn it upside down so that I don't lose any of my liquids. And then open the tap to release that pressure. Other bits of details then are at the end. Combining the organic layers, which we talked about, and then evaporate the solvent. This is if I want to get my solute. So obviously what I end up with is, say for example, we put it in a beaker, and the beaker contains my organic solvent, and in there I will have my X dissolved. But if I want X on its own without the organic solvent, I need to remove that organic solvent by evaporation. And the reason it says there without heat is because organic solutes, we know that organic products tend to be very volatile. So if we heat it, we'll end up losing our solute as well as our solvent. How then do you evaporate a solvent without heating, you might ask? Well, you don't need to know this, but you use something called a rotary evaporator, which looks a little something like this. And so what you do is you put your solution in here. So that'll be your organic solution of X dissolved in your organic solvent. Okay, and then what happens is this thing, it starts spinning round. This flask starts spinning round. This is a water bath, which you can heat slightly to get this to happen. This spins round, and as it spins round, because our organic solvent is so volatile, then it evaporates. It goes up this tube and up this sort of glass coil thing, and it will then condense in this condenser, and the organic solvent is collected then in this flask. And what you'll be left with at the bottom of this flask is then your organic solute X. You don't need to know that, but that's how you remove an organic solvent without heating. So a little bit further up the page, it talks about multiple solvent extractions versus single solvent extractions. What it says is that solvent extraction works better. And what we mean by that is that it extracts more of our organic solute from the aqueous layer into the organic layer. When we do multiple extractions rather than one single extraction. So what it means is that rather than doing one extraction with, say for example, 100 centimeters cubed of our organic solvent, if we split that 100 centimetres cubed into 2 equal portions of 50 centimetres cubed and do the extraction twice, then I will get much more of my solute extracted from that. Even better, if I split the 100 centimetres cubed up into 4 25 centimetre cubed portions and carry the extraction out 4 times, each with 25 centimetres cubed of my organic solvent, rather than doing it just once with 100 centimetres cubed. So you're using the same overall volume of your organic solvent, but it works much better if you split it up into smaller portions and do it a number of times. And we'll see that with our later calculations. And on that note, when you have calculations involving solvent extractions, it may be done as a single extraction, which is simpler, or it may be done as a multiple extraction, which involves a little bit more work. So these types of calculations would compare most similarly to KP calculations, where you would be given, say for example, the initial number of moles and the value of KP, and then from that being asked to work out what your equilibrium moles are, or equilibrium partial pressure in the example of KP. So thinking about KC calculations, we would have used X to represent the equilibrium concentration of one of our reactants. So we don't know what the equilibrium concentration is, and so we need to represent it by an unknown, and we choose X to do that. Because we tend to use mass instead of concentration with KD, X will represent the equilibrium mass of the solute in the organic layer. So let's have a look at this example. And you can see that I've got exactly the same 5 values on the left hand side: initial and reacting mass, followed by equilibrium mass, and then the volume of solvent, which we will use to calculate the equilibrium concentration. Okay, so here we've been given the value of KD. You can see that it is called the partition coefficient. That's just another name for KD. So the partition coefficient of A between ether and water is 4. And again, ether is our organic and water is obviously our aqueous. What we can see is that initially we have 5 grams of A dissolved in 100 centimetres cubed of water. The initial mass of A in ether is going to be 0 because it is originally just all dissolved in water. How much of it will move into the ether layer? Well, we don't know that, so we represent that by using plus X. So X grams of A are going to move into the ether layer when we shake them together. That means that X grams of A are going to be lost from my water layer. So the equilibrium mass of A in water is going to be 5 minus X, and in ether is going to be just X. Volume of solvent I need to get from the question. You can see that I've got 100 centimetres cubed of water and just 10 centimetres cubed of my ether. Equilibrium concentration, remember, is mass over volume. So equilibrium concentration of A in water is going to be 5 minus X over 100. And in ether, it's going to be X over 10. What I do now is plug these values of equilibrium concentration into my expression for KD. KD is the concentration of A in ether over the concentration of A in water. The question tells me that my KD value is 4.0, and that is equal to the concentration of A in ether, which we've written as X over 10, divided by the concentration of A in water, which is 5 minus X over 100. To simplify this down a bit, I'm going to move this, what's on the bottom half of my equation, to the left hand side. Because it's on the bottom half, it's dividing on the right, it's multiplying on the left. So it's going to be 4 times by 5 minus x over 100. And that's going to equal x over 10 on the other side. Multiplying out that bracket first of all. 4 times 5 is 20. And 4 times x is 4x, and it's minus x, so it's minus 4x over 100 equals x over 10. At this point, I can simply cross multiply. And so I'm going to have 10 multiplied by 20 minus 4x. So 10, 20 minus 4x is equal to 100 times x. Multiplying out that bracket, 10 times 20 is 200. 10 times minus 4x is minus 40x is equal to 100x. I want to bring my x's to the same side, so I move 40 to the other side. Because it's minus on the left, it's going to be plus on the right, so it's 200 is equal to 100x plus 40x. Simplify that down, you've got 140x. And then to work out what the value of x is, I do x is 200 divided by 140. That gives me a value of x as 1.43. So just as before, this is not our final answer. The question asks us to work out the mass extracted into the ether. Well, at equilibrium, the mass in the ether was x. And so it's simply what we extracted into the organic layer, the ether layer, was 1.43 grams of x. Now, obviously, it has worked out that this is the same answer, but don't just assume that x is your final answer, because it could have asked you for the mass in the water, and we can calculate that now. Mass in water, and we represented that by 5 minus x, which would be 5 minus 1.43, which is 3.57 grams in the water. So don't just assume x is your final answer, and also you need to add units to it, which are grams, because it's the mass extracted into the organic layer. So as we said previously, solvent extraction works much better with multiple extractions versus one larger single extraction. And we're going to have a look at calculations that will show that. These calculations are just slightly more complicated, but all you have to do is do the exact same calculation twice, but using the mass remaining in your water from the first extraction as your initial mass for the second calculation. And we'll see that when we come to the calculation. So the first example you have there is a single extraction. And then we'll do a multiple extraction of the same example and see how it compares. So what you can see is that we've got solute X, and it's originally dissolved in 20 centimetres cubed of water. So let's set out our working out first of all. So we'll have X in water versus X in our ether, which is our organic solvent mentioned in the question. And down the side, as previously, we'll have our initial mass, our reacting mass, our equilibrium mass, the volume of the solvent, and the equilibrium concentration. So initial mass, firstly, we've got 20 grams of solute X dissolved in water. Just be careful which one it starts in. That means if initially it's all in the water, we'll have none in the ether. We don't know what our reacting mass is, and so we can just take that as plus X in the ether layer. So it's saying that X grams of X is going to move into the ether layer, which means that we're going to lose X grams from the water layer. So equilibrium mass of water we can represent by 20 minus X, and the equilibrium mass in ether is going to be simply X. Looking at our solvent then, we can see that we've 20 centimetres cubed of water and 100 centimetres cubed of ether. Concentration, again, mass over volume. So we're simply doing 20 minus X over 200 for our concentration in water, and X over 100 for our concentration in ether. Now it's time to put those into our KD expression. So remember that KD is equal to the concentration of X in our ether over the concentration of X in water. We've been told in the question that KD is 4, and we've represented the concentration in ether as X over 100 and the concentration of X in water as 20 minus X over 200. The working out from this point is exactly the same as was done in the previous question, so perhaps you could stop the video and give it a go yourself, and then I will go through the rest of it. Okay, so what we want to do is move this to the other side of the equation to make it a bit simpler. So it's divided on the right, so it's going to be multiplied on the left. And so we're going to have 4 multiplied 20 minus X over 200 is equal to X over 100. Multiplying out this bracket, we get 4 times 20 is 80 minus 4 times minus X, which is 4X, over 200 is equal to X over 100. Again, as we did before, just cross multiply. And we end up with 200 times X is 200X on one side. And then we have 80 minus 4X times 100 on the other side. So that's 100 times 80 minus 4X. Multiply out that bracket, you should get 200X is equal to 8,000 minus 400X. Again, I want to bring my x's to the same side of the equation. So bring my minus 400x over to the left hand side. It's minus on the right hand side, so it needs to be plus on the left hand side. So 200x plus 400x is equal to 8,000. $600x then is equal to 8,000, and so x is 8,000 over 600, which equals 13.33. Again, don't just assume that's the answer, but we are looking for how much was extracted into the ether layer, and we did represent that by x, so the mass in the ether layer is just 13.33 grams. That is the calculation if we were to do just one single extraction. On the next page, we'll do the same example, but using 2 smaller volumes of our organic solvent. So the second part of the question is asking us to compare how much would be extracted into the ether layer if we were to use 2 smaller portions of our organic solvent. So you can see with the previous question that I had 100 centimetres cubed of ether. If I want to use two equal volumes of the ether, if they have to be equal, I need to do 100 over 2, which is 50 centimetres cubed. So from that, I can see that I'm going to have two 50 centimetre cubed portions of my organic solvent. Now, you might want to take a blank page for this. This is going to involve quite a wee bit of working out. So I'm doing my calculation exactly as before, but using a volume of organic solvent of 50 centimetres cubed. So my working out will involve me writing X in water versus X in the ether. And down the left hand side, as before, will be my initial mass reacting mass, equilibrium mass, volume of solvent, and equilibrium concentration. Okay, so initially we have, and you need to go back to 1A on page 55 for this. Initially we have 20 grams of solute X dissolved in water and none in our ether. Our reacting mass, again, we don't know that. We'll take it as plus X for ether, which means that X grams of X are going to be lost from the water. That means that the equilibrium mass of X in water is going to be 20 minus X. And in ether, it's simply going to be X, because remember, equilibrium is initial plus reacting. The volume of our solvent, as before, we had 200 centimetres cubed of water, but this time the volume of our organic solvent is 50 centimetres cubed. That means the equilibrium concentration is simply mass over volume, so it's 20 minus X over 200 for X in water, and X over 50 for the concentration of X in ether. Now all we have to do is put this in our expression for Kd. Remember, Kd is the concentration of X in ether over the concentration of X in water. We are told in the question that Kd is 4, and then we just substitute our concentrations of X in water and ether into our expression. Again, the calculation is exactly the same, so if you want to pause it, see if you can work it out by yourself, and then I'll go through it. So the concentration of X in ether is X over 50. Concentration of X in water is 20 minus X over 200. I want to bring this to the other side, and I get 4 multiplied by 20 minus X over 200 is equal to X over 50. Multiplying out that bracket, I get 80 minus 4X over 200 equals X over 50. Want to cross multiply in order to get X's on the same side. So first of all, I do 200 times X equals 50 times 80 minus 4X. Multiplying out that bracket, 50 times 80 is 4,000. 50 times minus 4 is minus 200x. Bringing x's to the same side, I've got 200x plus 200x is equal to 4,000. 400x is equal to 4,000. And so x is 4,000 over 400, which means that x is equal to 10. But what does that actually mean, x is equal to 10? What that means is that the mass in the ether layer we said was equal to x, which is 10 grams. So out of the 20 grams of my original x, I've extracted 10 grams of that into the ether. So now I need to work out how much is left in the water layer. So mass remaining in the water layer is going to be my original 20 minus x, and we can get that from our expression of the equilibrium mass of water. So it's 20 minus x, which is 20 minus 10, which is 10 grams. Obviously, the mass remaining in the water plus the mass in the ether need to add up to the total original mass of x that we added in. So we added 20 grams of x originally. What we're saying is that 10 grams has been extracted into the ether, which leaves 10 grams remaining in the water. And what we're now going to do is we're going to take our water layer and we're going to add in another 50 centimetres cubed of organic solvent and see how much we can extract from that. So if you remember, as I talked previously about this method of extracting, we wash it with or mix it with the organic solvent. Some of it will move into the organic solvent, and that's what's happened here. I'll then separate these two layers in a separating funnel. So I'll put this 10 grams that's in the ether, I'll put that off to the side somewhere. And then I'm taking this layer, my aqueous layer containing a further 10 grams of x, and I'm going to wash it again with a further 50 centimetres cubed of organic solvent. If you're not quite sure what I'm doing, then go back to the part where I talk about this method of solvent extraction. What we're trying to do is get our organic solute, which is dissolved in the aqueous solvent, and we're going to try and get it into the organic solvent so then it can be removed from that. So the previous working out was for the first washing, and we talk about this word washing, that just means, you know, mixing it with the organic solvent. So this working out is now the second washing. And again, we need to set out our working out as before. So we've got x in water versus x in ether. Down the left hand side, same working out, initial mass reacting mass, equilibrium mass, volume of solvent, and equilibrium concentration. Okay, so thinking of my initial mass now, what I worked out from the first washing. So from the first washing, after the first washing was complete, 10 grams remained in the water. And we worked out that out in our previous calculation. So that means I take this as my initial mass in the water. So what I've done is I've taken my water layer and I'm now washing it with a further 50 centimetres cubed of my ether. So that's my initial mass of x in the water layer. And that's the only thing that's different about these types of calculations. You need to know which value to use as your initial mass for your second washing. So I initially have 10 grams in my water, and so that means I have no x in my ether layer initially. I don't know what my reacting mass is, so I take that as plus x for ether and minus x grams of my x will be removed from the water layer. Equilibrium mass is just initial plus reacting, so it's going to be 10 minus X for the water layer and X for the ether layer. Volume of the solvent, again, it hasn't changed for my water layer. It's just the original 200 centimetres cubed of water. And in the ether, remember, we're using two 50 centimetre cubed portions. Equilibrium concentration is mass over volume. It's going to be 10 minus X over 200 for the water layer and X over 50 for the ether layer. Again, as before, I'm just going to plug this into my expression for KD. Again, you could try this yourself and then see how you get on. So KD is the concentration of X in your ether layer over the concentration of X in your water layer. I'm told in my question that KD is 4, that hasn't changed. The concentration of X in ether is X over 50. Concentration of X in water is 10 minus X over 200. Again, as before, I'm just going to bring this to the other side. So that's 4 times by 10 minus X over 200 is equal to X over 50. Multiplying out that bracket, I get 40 minus 4X over 200 is equal to X over 50. Again, as before, just going to cross multiply at this stage. So I get 200 times X is equal to 40 minus 4X over 50, or times by 50, which is 50 times by 40 minus 4X. Multiplying out that bracket, 50 times 40 is 2000, and 50 times by minus 4X is minus 200X. Bringing this to the other side so that all my X's are on the same side, I get 200X plus 200X is equal to 2000. Simplify that down, you've got 400X is equal to 2000, and so X is 2000 over 400, which equals 5. So what does that value of X equal 5 mean? Well, look back at your equilibrium concentrations. What that means is that the mass I've now extracted into my ether layer, we represented that by X. So that means I've extracted 5 grams of X into my ether layer. So how do I know that I've got more of X extracted using 2 smaller extractions rather than 1 larger extraction? Well, I can work out from this with the total mass of X that I have extracted. So the total mass of X extracted is going to be the mass I extracted from my first washing. And if you look back to the first part of this calculation, we extracted 10 grams from the first washing. And we have just worked out that we have extracted 5 grams from the second washing. That gives me a total of 15 grams of X extracted. Compare that to your answer from 1A, which we did on page 55. And we found that we extracted 13.33 grams from one washing of 100 centimetres cubed. And so you can see that we extracted 15 grams from 2 times our 50 centimetres cubed portions. Versus 13.33 grams extracted from 1 times 100 centimetre cubed portion. So yes, we have used exactly the same volume of organic solvent of our ether, but the second time we did it with 2 50 centimetre cubed portions, which has extracted a larger mass of X. So that's us at the end of our equilibrium topic, you'll be glad to hear. So you're now at the stage where you can do the remaining questions in the rest of your booklets on page 57 to 59. So have a go at those and yes, have fun.